Good day and welcome to Big Bad Tech. I'm your instructor Jim Pytel, and today's topic of discussion is using an oscilloscope to measure phase shift. Our objective is to learn how to use an oscilloscope to measure the relative phase shift between two waveforms displayed on the same horizontal time axis. We'll examine traditional manual calculation methods, as well as time-saving automated methods offered by some modern oscilloscopes. If you recall, at the very end of the AC Ohm's Law lecture, available at the Big Bad Tech channel, we learned that digital multimeters in AC voltmeter and AC ammeter mode are traditionally limited to measuring effective or RMS value only and do not customarily measure relative phase shift. Today we'll learn to experimentally measure relative phase shift between two waveforms using an oscilloscope. For the purposes of today's lecture, we'll be making use of the Tektronix TBS 1032B digital oscilloscope. This is in no way meant to be neither an exhaustive review of this tool nor an endorsement of this particular manufacturer or model. I only wish to present the functions of interest on a representative example so the viewer can gain some practical exposure to these functions and interpret the manner in which results are displayed. If you recall, an oscilloscope is a graphical means of displaying voltage as a function of time, where voltage is the vertical dimension and time is the horizontal dimension. By properly scaling, positioning, and triggering an individual waveform under inspection, various properties about that individual waveform can be measured, including but not limited to peak, peak-to-peak, effective or RMS value, period, and frequency. In addition to these properties related to individual waveforms, modern oscilloscopes like the Tektronix TBS 1032B digital oscilloscope are often multi-channel devices, meaning they can simultaneously display two or more voltage waveforms on the same screen. This ability to simultaneously depict more than one waveform conveniently lends itself to measuring the relative phase shift between the waveforms under inspection. Let's examine the means of measuring relative phase shift using traditional manual calculation methods first. Manual calculation, in contrast to the automated methods I'll demonstrate in a moment, are open to some interpretation. However, the values obtained should be close to your anticipated results. While admittedly primitive, these techniques are absolutely essential to the conceptual understanding of oscilloscopes and AC circuit theory and are not to be dismissed. You never know when someone might ask you to do this on a quiz or an exam. Hint, hint. Manual measurement using an oscilloscope is really just a game of unit conversion. The advantage being, given vertical and horizontal sensitivity are independently adjustable, a user has a degree of control over the conversion factor. Additionally, given a trace can be repositioned left, right, up, and down in the oscilloscope screen, a user can take advantage of various markers to obtain more accurate results. Since today's lecture deals exclusively with measurement of the relative phase shift between two waveforms, our principal dimension of concern is the horizontal time axis. Although, as we'll learn in a moment, rescaling the vertical axis can sometimes increase our precision. You'll note this oscilloscope is currently scaled using a vertical sensitivity of 2 volts per division on both channel 1 and channel 2. Additionally, it has a horizontal sensitivity of 500 microseconds per division. You note within each vertical and horizontal division, 5 subdivisions exist, where each subdivision represents 1/5 of a full division. Given the current vertical sensitivity, each vertical subdivision represents 1/5 of 2 volts, or 0.4 volts. Similarly, given the current horizontal sensitivity, each horizontal subdivision represents 1/5 of 500 microseconds, or 100 microseconds. When a sinusoidal voltage waveform is displayed on channel 1, we can use the scaled vertical and horizontal markers to measure various properties. By all means, pause the lecture and see if you can determine the peak value, the effective value, the period, and the frequency of this waveform. If you're tracking, you should have obtained the following values. Looks like this first waveform in yellow peaks at, let's say, 3.6 divisions above the horizontal axis. Given the current vertical sensitivity of 2 volts per division, this corresponds to a peak value of 3.6 divisions times 2 volts per division, or approximately 7.2 volts. This peak value corresponds to an effective value of 7.2 volts over square root 2, or roughly 5.1 volts. You'll note this sinusoidal waveform isn't perfectly symmetric in that its positive peak is slightly larger than the negative peak. However, let's just go with these figures. Note the 2 zero crossings going positive appear to be separated by, let's say, roughly 6.7 divisions. Given the current horizontal sensitivity of 500 microseconds per division, this corresponds to a period of 6.7 divisions times 500 microseconds per division, or approximately 3.35 milliseconds. It can be demonstrated that by taking the inverse of this measured period value, that our frequency is 1 over 3.35 milliseconds, or approximately 298.5 hertz. The astute and observant among you may have noted that the oscilloscope has already gone to the trouble of performing this calculation and is displaying a frequency of 299.2 hertz, essentially 300 hertz, in the lower right-hand corner. Key to the measurement of phase shift is your understanding that a sinusoidal waveform undergoes a complete cycle in 360 degrees. Given this waveform has a period of 3.35 milliseconds, it can be rightly said that 360 degrees equals 3.35 milliseconds, and this conversion factor establishes a means of translating between time and degrees and vice versa. Let's put these figures aside and do the same thing for a second waveform on channel 2 in blue. Multi-channel oscilloscopes allow a user to toggle between channels or to display both waveforms simultaneously. Here I've turned off channel 1 and turned channel 2 on. You note the oscilloscope is still scaled as previously using a vertical sensitivity of 2 volts per division and a horizontal sensitivity of 500 microseconds per division. By all means, pause the lecture and see if you can determine the peak value, the effective value, the period and frequency of this second waveform. If you're tracking, you should have obtained the following values. It looks like the second waveform in blue peaks at, let's say, 1.8 divisions above the horizontal axis. Given the current vertical sensitivity of 2 volts per division, this corresponds to a peak value of 1.8 divisions times 2 volts per division, or approximately 3.6 volts. This peak value corresponds to an effective value of 3.6 volts over square root 2, or roughly 2.5 volts. Despite being shifted from a primary division, note the two zero crossings going positive still appear to be separated by roughly 6.7 divisions. Given the current horizontal sensitivity of 500 microseconds per division, this again corresponds to a period of approximately 3.35 milliseconds. It can again be demonstrated that by taking the inverse of this measured period value, that our frequency is approximately 298.5 hertz. This is the same frequency we obtained for our first waveform. Again, note the oscilloscope has already gone to the trouble of performing this calculation and is displaying a frequency of 299.3 hertz, essentially 300 hertz in the lower right-hand corner. Let's put these figures aside and discuss relative phase shift. To manually calculate the relative phase shift between these two waveforms, one needs to display them simultaneously. To do so, both channel 1 and channel 2 are turned on. Note both channels are displayed using a vertical sensitivity of 2 volts per division and a horizontal sensitivity of 500 microseconds per division. It is immediately evident the yellow waveform on channel 1 is larger than the similarly scaled blue waveform on channel 2 due to the properties we previously measured. One can also make two equally relevant observations about these waveforms in terms of phase shift. Note the blue waveform on channel 2 appears to lag the yellow one on channel 1. Similarly, one can also state that the yellow waveform on channel 1 leads the blue waveform on channel 2. This duality is inherent to the relative nature of two waveforms in that one can only describe a repetitive waveform's position with respect to another. Relativity, as the name implies, relates two quantities with one another, and importantly implies that one of the pair is used as a frame of reference from which the other is measured. Let's just assume the yellow waveform on channel 1 is our reference, and we wish to determine the phase shift of the blue waveform on channel 2 with respect to the yellow waveform on channel 1. The phasor representation of the yellow waveform on channel 1, since it's our reference, is 5.1 volts at an angle of 0 degrees. Note the zero crossing going positive of the blue waveform appears to lag the yellow waveform by 0.6 divisions. Given our current horizontal sensitivity of 500 microseconds per division, this corresponds to a time shift of 0.6 divisions times 500 microseconds per division, or 300 microseconds. Now we need to convert this time shift to degrees. Given both these waveforms complete a 360-degree cycle in 3.35 milliseconds, a unit conversion shows that the blue waveform on channel 2 is lagging the yellow waveform on channel 1 by 300 microseconds times 360 degrees divided by 3.35 milliseconds, or approximately 32.2 degrees. The phasor representation of the blue waveform on channel 2 is therefore 2.5 volts at an angle of negative 32.2 degrees. In summary, there is a relative phase shift at 32.2 degrees between the two waveforms. Given this phase shift is relative, it can be said that the blue waveform lags the yellow waveform just as easily as it can be said that the yellow waveform leads the blue waveform. Now, both these channels of the oscilloscope are currently scaled using a vertical sensitivity of 2 volts per division. While this level of magnification does permit display of the complete waveform and easy measurement of properties like peak value and period, one can zoom in to gain an enhanced perspective of just the relative phase shift between these waveforms. If we change the vertical sensitivity of channel 1 to 500 millivolts per division, notice the top of the first waveform in yellow disappears off the display. However, the zero crossing going positive is crisper and far more recognizable. Note the crossing doesn't actually happen at a primary division like I assumed it did earlier. This may have induced a tiny error in our previous calculation. One can horizontally reposition the oscilloscope display to place the zero crossing going positive of the yellow waveform right on a primary division. Note I have not changed the magnitude of the first waveform in yellow. I've just rescaled it. The second waveform in blue looks comically small because it's still using our previous scale of 2 volts per division. If we change the vertical sensitivity of channel 2 also to 500 millivolts per division, again notice the top of the second waveform in blue disappears off the display. However, the zero crossing going positive is crisper and far more recognizable. Despite the increased ease of measurement using this rescaled display, it looks like the two waveforms are still separated by 0.6 divisions. Given our horizontal sensitivity is still set to 500 microseconds per division, this still represents a phase shift of 32.2 degrees. In an effort to increase the precision of the phase shift measurement, one is also free to adjust the horizontal sensitivity. However, this often necessitates a user horizontally reposition the display to keep both zero crossings going positive on the screen. If we change the horizontal sensitivity to 100 microseconds per division, notice the two waveforms are now separated by, let's say, 3 divisions. Given our horizontal sensitivity is set to 100 microseconds per division, this still represents a time shift of 3 divisions times 100 microseconds per division, or 300 microseconds. As previously, a 300 microsecond time shift inside a waveform with a period of 3.35 milliseconds has a phase shift of 32.2 degrees. Using this increased level of magnification, we still arrived at the same result. However, if there was any doubt previously, it's most certainly been dispelled. Again, note when rescaling to such a comical degree, it's often necessary to horizontally reposition the display so both zero crossings going positive remain on the screen. If you're too zoomed in or too zoomed out, you'll often get a distorted view of what you're actually looking at. Really, that's all there is to be said about manual calculation of phase shift using an oscilloscope. It's a game of unit conversion, and one can reposition or rescale the output to get the best results. Let's test your understanding of manual calculation of phase shift using an oscilloscope with the following example problems. For each oscilloscope display, calculate the relative phase shift between the two waveforms given the vertical and horizontal sensitivity as displayed on the screen. For the purposes of this exercise, let's assume the yellow waveform on channel 1 is our reference. We're being asked to determine if the blue waveform on channel 2 leads or lags it, and if so, by how much. Since these problems necessitate some attention to detail, let's perform these examples one by one. By all means, pause the lecture and try to determine the relative phase shift between these two waveforms on your own. If you're tracking, you should have obtained the following value. The first example problem shows two waveforms, both with a period that stretches, let's say, 6.1 divisions. Given the horizontal sensitivity of 2.5 milliseconds per division, this correlates to a period of roughly 15.3 milliseconds. One could also back-calculate period using the conveniently available frequency measurement of 64.6 Hz in the lower right-hand side. Doing so yields a period of approximately 15.5 milliseconds. Let's go with this figure since our manual measurement might be off. These waveforms appear to be separated by, let's say, 0.8 divisions. Given a horizontal sensitivity of 2.5 milliseconds per division, this correlates to a time shift of 0.8 divisions times 2.5 milliseconds per division, or 2 milliseconds. This time shift correlates to a relative phase shift of 2 milliseconds times 360 degrees divided by 15.5 milliseconds, or approximately 46.5 degrees. It can be said that the blue waveform leads the yellow waveform by approximately 46.5 degrees. Here's our second display. It appears to be zoomed in on just the right spot. Although the full waveforms aren't available for inspection, note the conveniently available frequency measurement in the lower right-hand side. Hint, hint. By all means, pause the lecture and try to determine the relative phase shift between these two waveforms on your own. If you're tracking, you should have obtained the following value. The second example problem shows two waveforms, both with a frequency of 180.4 Hz, which corresponds to a period of approximately 5.54 milliseconds. The waveforms appear to be separated by slightly more than 4.1 divisions. Let's say 4.12 divisions. Given the horizontal sensitivity of 250 microseconds per division, this correlates to a time shift of 4.12 divisions times 250 microseconds per division, or approximately 1.03 milliseconds. This time shift correlates to a relative phase shift of 1.03 milliseconds times 360 degrees divided by 5.54 milliseconds, or negative 66.9 degrees. It can be said that this blue waveform lags the yellow waveform by 66.9 degrees. Finally, here's our third illustrated example problem. Again, it appears to be zoomed in just the right spot. By all means, pause the lecture and try to determine the relative phase shift between these two waveforms on your own. If you're tracking, you should have obtained the following value. The third example problem shows two waveforms, both with a frequency of 224.6 Hz, which corresponds to a period of approximately 4.45 milliseconds. The waveforms appear to be separated by slightly less than 1.2 divisions. Let's say 1.19 divisions. Given the horizontal sensitivity of 250 microseconds per division, this correlates to a time shift of 1.19 divisions times 250 microseconds per division, or approximately 297.5 microseconds. This time shift correlates to a relative phase shift of 297.5 microseconds times 360 degrees divided by 4.45 milliseconds, or 24 degrees. It can be said that the blue waveform leads the yellow waveform by 24 degrees. Alright, hopefully you did well on those illustrated example problems. If you're feeling confident, by all means try out this bonus round problem. If you truly understand the measurement of phase shift using an oscilloscope, you should be able to do this in reverse. Given this phasor diagram, valid at a frequency of 249.6 Hz, where V1 in yellow has a phasor equivalent of 4.7 volts at an angle of 0 degrees, and V2 in blue has a phasor equivalent of 2.7 volts at an angle of positive 27 degrees, determined by how many divisions they'll be separated when displayed on an oscilloscope with a horizontal sensitivity of 500 microseconds per division. I say again, given two waveforms with a frequency of 249.6 Hz, known to have a relative phase shift of 27 degrees between them, determined by how many divisions they'll be separated when displayed on an oscilloscope with a horizontal sensitivity of 500 microseconds per division. By all means, try this on your own. If you're tracking, you should have obtained the following value. Key to the solution of this problem is a two-step unit conversion. Given our previously developed skill set, you should be able to convert a phase shift in degrees to a time shift in units of seconds. The next step is to simply convert this time shift in units of seconds to units of divisions given the established horizontal sensitivity of 500 microseconds per division. Allow me to demonstrate. A waveform with a frequency of 249.6 Hz has a period of approximately 4 milliseconds. Given a phase shift of 27 degrees, this correlates to a time shift of 27 degrees times 4 milliseconds divided by 360 degrees, or 300 microseconds. Given a horizontal sensitivity of 500 microseconds per division, this correlates to a separation of 300 microseconds over 500 microseconds per division, or 0.6 divisions. Let's see if we're correct. When two waveforms with a frequency of 249.6 Hz and a relative phase shift of 27 degrees between them are placed on the oscilloscope using a horizontal sensitivity of 500 microseconds per division, we do indeed observe a separation of approximately 0.6 divisions between them. This goes to show you that you should be capable of predicting how waveforms relate to one another in advance. In summary, do the calculations first. If your observed results don't match your calculations, perform a tactical retreat and reassess your as-built circuit, or revisit your calculations. Moving on. If the manual calculation of phase shift seems low-tech and somewhat inaccurate, you're right. A lot of the inaccuracy for manual calculation of phase shift stems from differences in interpretation. However, this method should still yield results inside an expected range. Luckily, modern oscilloscopes offer more sophisticated means of measuring data. These automated methods are quicker and more accurate, however, necessitate a bit of learning curve because each oscilloscope manufacturer and model does it ever so slightly different. Despite their increased accuracy and speed, these shortcuts don't mean you can forget how to calculate phase shift manually. You never know when someone will ask you to perform the aforementioned procedure on a quiz or an exam. Hint. Hint. The Tektronix TBS 1032B offers two means of automated data measurement: cursors and automatic. Let's examine cursors first. Let's explore application of the cursor measurement feature by way of an example. Let's use the same two waveforms we initiated this lecture with. Both waveforms have a frequency of approximately 300 Hz, and the blue one on channel 2 appears to be lagging the yellow one on channel 1 by a certain distance. If you recall correctly, our earlier manual calculation method yielded a time shift of 300 microseconds and a phase shift of 32.2 degrees between these two waveforms. We could take another manual measurement and do the math as previously. However, the cursor tool can at least do the measurement for us. Allow me to demonstrate. Cursors are accessible via the Cursors button in the Operations group. Cursors come in two types: amplitude and time. For phase shift measurements, we need to select the time cursor inside the cursor menu. First, select cursor 1 and drag it along the first waveform to the zero crossing going positive using the multifunction knob. Then select cursor 2 and drag it along the waveform to the zero crossing going positive of the blue waveform using the multifunction knob. Note the cursor is currently tracking channel 1, however user can toggle between the two channels for accurate tracking purposes. Looks like cursor 1 is at negative 60 microseconds and cursor 2 is at 240 microseconds. The differential between them appears to be 300 microseconds. Too easy. The cursor tool shows our earlier time measurements were pretty close. This time shift correlates to a relative phase shift of 300 microseconds times 360 degrees divided by 3.34 milliseconds, or 32.3 degrees. It can be said that the blue waveform lags the yellow waveform by 32.3 degrees. In short, the cursor tool does part of the work for you. If only we could say the same thing about your lab partner. But wait, that's not all. Modern oscilloscopes like the Tektronix TBS 1032B have an even easier measurement technique for the morbidly lazy among you. If performing manual calculation isn't your style and dragging cursors around a screen seems too exhausting, you can always let the oscilloscope automatically measure phase shift for you. Press Measure in the Operations group. Inside the Channel 1 measurement menu, we are presented with a huge array of available automatic measurements. Navigate through the list using the multifunction knob and select Phase way down towards the bottom. Inside the Phase submenu, choose Channel 1 minus Channel 2. The automated phase measurement shows that the blue waveform on Channel 2 is lagging the yellow waveform on Channel 1 by 30.3 degrees. Extremely close to our manually calculated and our cursor-assisted calculation results. In short, all methods yielded reasonably accurate results, only this automated method did so quickly without the necessity of resorting to calculations. You'd think automated phase measurement would be humanity's single greatest technological innovation since they replaced the turd brown M&M with the blue one, but it isn't because this feature is admittedly a little clunky for a couple of reasons. One, it's super hard to find because it's buried way at the bottom of the heap of measurement options and is hidden in its own secret submenu. And two, this feature is about as smart as a goldfish. Recall we initially assumed the yellow waveform on channel 1 was our reference waveform and calculated the relative phase shift of the blue waveform on channel 2 with respect to this reference. Beware of occasions in which your frame of reference differs from that assumed by the oscilloscope. Regarding the goldfish level of intelligence exhibited by this feature, also be aware of occasions in which a waveform clearly lagging by, let's say, 20 degrees is mistakenly measured as one leading by 160 degrees, or occasions in which a waveform clearly leading by, let's say, 15 degrees is mistakenly measured as one lagging by 165 degrees. Regardless, if you're well versed in phase shift as I expect you to be, you should be able to interpret these results. In short, Don't blindly trust machines. If there's anything I learned from watching The Matrix, is that they're hell-bent on enslaving us. Do the calculations first and confirm your observations are within your expectations. Trust no one, least of all your lazy lab partner. I've got a sneaking suspicion they're actually a robot programmed to slow you down. Only way to find out for certain is to stick a screwdriver in their head. Alright, that's about it for phase shift measurement using an oscilloscope. Yes, there are other techniques one can use, specifically the Lissajous pattern, but I am not touching that amoeba-shaped blob with a 3.048 meter pole because it's really just an obstacle instructors trapped to the 1950s used to waste your time and frustrate you. Let it never be said that I labeled the Lissajous pattern ineffective, but rather unnecessary and unimportant when compared to other more direct and memorable techniques of phase shift measurement like those we discussed today. In conclusion, this lecture examined the means of manually calculating phase shift using an oscilloscope, as well as faster methods like cursors and user-selectable automatic measurements. Remember to review these concepts as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest, and we'll see you again during the next lecture of our series. Remember to tell your lazy lab partner about this resource, and be sure to check out the Big Bad Tech channel for additional resources and updates.